Welcome to the Naiditch Report. This report discusses the Big Bang Theory, not the TV sitcom, but the scientific theory about the origin of the universe. Think you understand the Big Bang Theory? It may seem straightforward, but it's surprisingly subtle. I'll discuss 13 common misunderstandings, each posed as a question. See how many you can answer correctly. First, a quick overview. According to the Big Bang Theory, the universe exploded into being about 13.8 billion years ago from an extremely hot, dense speck and has been expanding and cooling ever since. Note that, as commonly interpreted, this theory doesn't address what, if anything, occurred before the Big Bang, what it was that banged, or whether there were multiple Big Bangs. I'll briefly discuss a theory that addresses such issues at the end of this presentation. Beginning in the 1920s, Edwin Hubble and others discovered that our galaxy, the Milky Way, isn't all that exists. There are billions of other galaxies, each containing billions of stars. Furthermore, the galaxies are racing away from us with a velocity that is directly proportional to their distance. If you run the clock backward, the universe arose from a tiny source. The case for the Big Bang was settled when its afterglow, the cosmic microwave background, CMB, was accidentally detected in 1964 by Arno Penzias and Robert Wilson of Bell Laboratories. These physicists shared the 1978 Nobel Prize in Physics for this monumental discovery. Interestingly, it turns out we were unknowingly picking up the CMB for decades. Turn an old CRT television set between channels. About 1% of the static is from the CMB. The CMB shows our baby universe when it was only 380,000 years old. This is as far back in time that we can ever see. Electromagnetic radiation can't reveal an earlier time because the universe was opaque. The CMB fills the sky and reveals the universe when it was 1,000th its current size, 1,000 times its current temperature, and 1.3 billion times its current density. This image of the CMB is from the Planck Space Telescope that produced its first all-sky image in 2010. The color variations show the temperature variations, the blue being the coolest. These temperature variations are extremely small, only 1 part in 100,000. The CMB seeded the large-scale structures of the universe: galaxy clusters, voids, sheets, and filaments. A common misunderstanding is to think of the Big Bang as a normal explosion. It wasn't. A normal explosion happens at a specific location. The shrapnel expands outward into the surrounding space and gets sparser. This isn't the case with the Big Bang. So here is the first question. According to the Big Bang Theory, on the cosmic scale, the distance between galaxies is increasing, but the galaxies themselves aren't moving. How is this possible? The answer is that the Big Bang isn't an explosion in space, but the expansion of space itself. The most common way to explain this counterintuitive claim is by using the inflating balloon analogy. Notice that the galaxies aren't moving on the balloon surface, but are carried along by the expanding rubber surface of the balloon. In a similar manner, on a cosmic scale, the galaxies aren't moving away from one another. It's the space between them that is expanding. Expanding space was shown to be possible in 1915 by Einstein's theory of general relativity. Space, actually space-time, is like a rubber membrane that can expand, contract, bend, warp, vibrate, and ripple. The moon, for example, orbits the Earth, not due to the pull of gravity, but because the moon is responding to the warped space-time generated by the Earth. As physicist John Wheeler famously stated, matter tells space-time how to curve, and curved space-time tells matter how to move. Beginning in 2015, gravitational wave observatories like LIGO and Virgo have detected gravity waves generated by the merger of massive objects, such as neutron stars and black holes. Gravity waves are ripples in space-time. The balloon analogy, as useful as it is, can't be taken too far. The balloon's two-dimensional surface represents our three-dimensional space. The balloon surface is all that exists. There is no inside or outside. The balloon expands, but not into any surrounding space. In addition, tension doesn't build up as the balloon stretches. Question 2. Because on the cosmic scale, everything is receding from us, are we at the center of the universe? As can be seen from this animation, from any point on the balloon surface, every galaxy is moving away. There is no point on the balloon surface that is the center of expansion. So, the Big Bang didn't happen at a particular location, but happened everywhere. Question 3. Why does the speed of expansion increase with distance? The galaxies on the balloon aren't moving, but are carried along by the expanding surface of the balloon. Doubling the distance doubles the speed because there is twice the amount of expanding surface. Question 4. Is it possible for the universe to be unbounded, yet finite in size? Yes, but we don't know if this is the case. Like the balloon surface, the universe could be unbounded, yet finite in size. If you started to travel in a straight line, the shortest distance between 2 points, you'll eventually return to the starting point. Question 5. If the universe is expanding, what is it expanding into? With the mathematics of general relativity, the universe expands without expanding into anything. An embedding space isn't needed. Question 6. If the universe is expanding, are galaxies, stars, and planets also expanding? Neither galaxies, stars, nor planets expand due to the expansion of space. These objects are held together by their own gravity, and the atoms making up these objects are held together by forces much stronger than gravity. So, on the small cosmic scale, the expansion of space is currently far too weak to counteract these forces. Question 7. If the recession velocity of a galaxy is directly proportional to its distance, why is the Andromeda Galaxy racing toward us? In 4 billion years, there is a chance it will collide with the Milky Way. Cosmic expansion is only significant on a very large scale. The Andromeda Galaxy is a cosmologically close neighbor that is gravitationally bound to us. This photo shows 2 galaxies colliding. Question 8. If the universe began as an infinitesimal speck and has been expanding for a finite amount of time, could it nevertheless be infinitely large? The universe is probably vastly larger than our visible universe. We don't know if the universe is infinite, but if it is, it started out infinitely large. Our visible universe could just be an expanding dot in an infinite expanse. Observers at each dot have their own observable universe that, given time, might overlap with ours. Question 9. If the universe is 13.8 billion years old, how can we, as astronomers claim, see 46.5 billion light years in every direction? If the universe was static, neither expanding nor contracting, then we would only be able to see 13.8 billion light years in every direction. However, during those 13.8 billion years the light was traveling, the universe has been expanding, so we can see objects that are now over 3 times that distance. Question 10. If galaxies are receding from us faster and faster the farther we look, would there be a point where galaxies are receding faster than the speed of light? Wouldn't this violate the cosmic speed limit? No object in space can accelerate to the speed of light, but space itself can expand faster than light. This doesn't violate Einstein's theory of special relativity. Question 11. Will the universe expand forever? Everyone thought that gravity would be slowing the universe's expansion. The question was whether there would be enough gravity to halt the expansion. In 1998, two independent teams were amazed to discover that the universe's expansion rate is actually accelerating. A kind of anti-gravity, which we now call dark energy, appears to be the repulsive property of space itself. This was anticipated by Einstein's cosmological constant. We have much to learn about the nature of dark energy. If dark energy is getting stronger over time, it'll eventually overwhelm the other forces. Galaxies, stars, planets, and even atoms will eventually be pulled apart in the Big Rip. Well, for those who hope the universe ends in fire, not ice, I got some good news. The Dark Energy Spectroscopic Instrument, DESI, created the largest 3D map of the universe and discovered that dark energy appears to be getting weaker over time. If this is true, the universe may eventually collapse and end in a big crunch. Question 12. What came before the Big Bang? Here is one possibility. Hopefully this is wrong, else we're in serious trouble. Actually, the Big Bang theory has little to say about the Big Bang itself. It describes what happened afterward. Einstein's theory of general relativity implies that the Big Bang began from a singularity of infinite density and temperature. The Big Bang created matter, energy, space, and time. According to general relativity, one cannot ask what occurred before the Big Bang because there was no before. It's like asking what is north of the North Pole. But relativity breaks down at the singularity. So let's briefly consider a theory that goes beyond the Big Bang theory. The theory of cosmic inflation was proposed by physicist Alan Guth in 1979. It specifies what occurred at the first moment of creation, before the Big Bang takes over. According to the theory of inflation, in less than a millionth of a trillionth of a trillionth of a second, the universe expanded by a factor of 1,000,000 trillion trillion. It's like in the tiniest fraction of a second, scaling up a molecule to the size of a galaxy. The fluctuations in a CMB are a giant image of quantum fluctuations when the universe was subatomic in size. These fluctuations seeded galaxy formation. The CMB shows that our universe is flat. Any curvature would distort the fluctuations. The theory of inflation explains why the universe appears flat. The rapid expansion flattened out any curvature that may have been present. The theory of inflation also explains why, on this large scale, the universe is the same everywhere and looks the same in every direction. Before inflation began, all parts of the universe were in contact with one another. Inflation also explains why the universe started out so hot. The heat was produced by the rapid growth spurt. Note that if the universe is vastly larger than what we can see, then it could nevertheless be curved. We can't detect this curvature from our limited perspective. Question 13. Was there just one Big Bang? Cosmologist Alexander Vilenkin and Andrei Linde realized that inflation's equations strongly suggest that the Big Bang wasn't a one-time event, but happened over and over again. Inflation implies our universe is just a bubble among infinite bubble universes that are continuously being created without end and perhaps without a beginning. If numerous universes exist, could they collide? A few cosmologists claim they have spotted a scar from such a collision in the CMB. Many, however, aren't convinced. Inflation provides novel answers to many questions. What happened before the Big Bang? There were an infinite number of Big Bangs, each triggered by their own inflation. Why are the laws of physics as they are? With the infinity of universes, all possibilities are realized. There is no particular reason for the specific laws that govern our universe. If these laws don't support our kind of life, we wouldn't be here to ponder such questions. How can the theory of inflation be tested? Inflation predicts inflation-generated gravity waves. These waves might be directly detected by the Laser Interferometer Space Antenna, LISA, scheduled to be launched in the mid-2030s. LISA will measure shifts in position that are less than the diameter of a helium nucleus over a distance of 1 million miles. Inflation's gravity waves might alternatively be indirectly detected by the Planck Space Telescope through the distinct polarization pattern in the CMB. As we have seen, the deeper one delves into the Big Bang theory, the stranger it seems. Let me end with a quote from Douglas Adams, the author of The Hitchhiker's Guide to the Galaxy. There is a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened.